Well, students, in the last class, we have started our discussion on interpolations. We have proved existence and uniqueness of the interpolating polynomial for a given data set. In this class, we will introduce two methods to construct interpolating polynomial for a given data set. One is called the Lagrange interpolation and another is called the Newton's interpolation. Let's quickly recall what we did in the last class. In the interpolation problem, we are given a table of data where you have x and y coordinates. X coordinate called nodes are generally given as distinct numbers, x0, x1 and so on up to xn, and y coordinate is called the values which can be generated from some functions at the points xi's, or it can be some observed values through some experiments. The question is, can we find a function whose graph passes through these points xi, yi? In particular, we are interested in constructing a polynomial whose graph passes through these points xi, yi. And such polynomials are called interpolating polynomials, and for a given set of data consisting of n+1 points, we intend to construct a polynomial of degree less than or equal to n in such a way that the graph of the polynomial passes through these points xi, yi. In other words, you have the polynomial Pn of x. If you put xi into the polynomial Pn, then you should get the value yi from the polynomial. So that's also called the interpolating condition. In the last class, we have seen that for a given set of data, we always get an interpolating polynomial and it is always unique. We will now go on with the construction of such polynomials. One way of doing it is using Lagrange form of interpolating polynomial. Another one is Newton's form of interpolating polynomial. You should note that whether it is Lagrange form or Newton's form, finally the interpolating polynomial will be the same because of the uniqueness. It is only the way we construct differs, but the final answer is the same. Let us take up this Lagrange form of interpolating polynomial. Given a data set like this, polynomial Pn of x given by sigma k equal to 0 to n yk lk of x, where lk is given by this formula, is an interpolating polynomial, and this form of writing this polynomial Pn of x is called the Lagrange form of interpolating polynomial. Let us prove this theorem. To prove this theorem, we have to show that the form that we assumed is indeed an interpolating polynomial. Once you achieve that, then uniqueness will tell you that Pn of x, which is the interpolating polynomial, is equal to this, right? So that will come automatically from the uniqueness condition. So we have to show that this form, which Lagrange proposed, is indeed an interpolating polynomial. To do this, we have to check those two conditions which are given as defining conditions for an interpolating polynomial. One is that the polynomial should be of degree less than or equal to n, because we are giving the data set with n+1 entries. Therefore, this should be a polynomial of degree less than or equal to n. And then we have to also show the interpolating condition, right? Once you show these two properties with this form of the polynomial, then it will become an interpolating polynomial for this data set. Once you achieve that, then uniqueness will tell you that this form is precisely equal to Pn of x, because already we assume Pn of x is an interpolating polynomial. Now you showed that this is also an interpolating polynomial for the same data set. Therefore, they should be equal because of the uniqueness. That is the idea. So let us go to prove that this form is indeed a polynomial of degree less than or equal to n. For that, first we will try to understand this one. This is generally called the Lagrange polynomial. This entire thing, after proving that it is an interpolating polynomial, this is called the Lagrange form of interpolating polynomial, or simply called the Lagrange interpolating polynomial. Please note the slight difference between these two names. Whenever I say Lagrange polynomial, it means it is this Li of x. Whenever I say Lagrange interpolating polynomial, it is this entire representation of the interpolating polynomial. Well, let us first try to understand how this Lagrange polynomial looks like. For each k equal to 0, 1, 2 up to n, you take one fixed k among these numbers. By keeping that k fixed, you are writing this polynomial. How it looks like? You see, x minus x naught, x minus x1, like that you keep on going. X minus xk minus 1. Now you will leave the term with k, right? Then jump to x minus xk plus 1. So you will not write x minus xk here, and then you keep on going till x minus xn divided by, now the same thing, instead of x you will put xk minus x naught, xk minus x1, like that you keep going till xk minus 1. Again, don't write xk minus xk, that becomes 0. Therefore, this entire thing will be infinity. That is why we are avoiding that, and jump to xk minus xk plus 1. That is what it means here, that I is not equal to k. Then xk minus xn. So this is how this polynomial looks like. Now you see what is the degree of this polynomial. The denominator is a constant, and since all the nodes are distinct, you can see that this is a non-zero constant, and you can see that the numerator is the product of n polynomials of degree 1, right? Why n? Because you have just skipped one term here. There are n plus 1 terms because you are going from 0 to n, but you skipped one term here in between. Therefore, there are n terms totally, and each is a polynomial of degree 1. Therefore, the numerator is a polynomial of degree n. So what is the first observation that we had is Lk of x is a polynomial of degree n for each k, right? There's another important observation that you can have. You take Lk of, in particular, you put one of the xi's, okay? Now, this I may be equal to k, or this I may be different from k. These are the two possibilities for this I, where I varies from 0 to n, and also k varies from 0 to n, right? Now, what happens if I is equal to k? If I is equal to k, then you are plugging in xi as an argument to Lk. Therefore, every term, instead of x, you will put xi in the numerator. So if I is equal to k, then this first term will become xi minus x naught, which is xk minus x naught, right? Because I equal to k for first case. Therefore, that will get cancelled with this. Similarly, this will become xk minus x1. That will again get cancelled with this. Like that, everybody gets cancelled. If you put x equal to xk, and therefore you will have 1 if I equal to k. Now coming to the next case, what happens if I is not equal to k? Then you can see that this I will be one among these terms, right? because here you involve all the terms other than k, right? If I is not equal to k, then that xi, which is supposed to sit instead of x here, will make one of these terms 0, right? And therefore, the entire polynomial will become a 0 polynomial, right? So that is how Lk of xi will look like. So this is in general a polynomial. When you substitute one of the node points, then depending on whether that node point index coincides with the polynomial's index k, in that case you will have the value of the polynomial as 1. If I doesn't coincide with this k, then you have 0. So how many Lagrange polynomials are there? Well, there are n+1 Lagrange polynomials, and they all satisfy this condition. So that is what I am writing here. Lixj, there's a slight change in the notation. I was explaining with Lk of xi. Here I wrote Li of xj, but the definition is same. If you put this, then Li of xj equal to 1 if I is equal to j, 0 if I is not equal to j. So this is a very important observation, because once you understand this, then the proof becomes very simple. Now go back to this and see, each of this is a polynomial of degree n. Therefore, their sum is a polynomial of degree at most n, right? Maybe depending on the values of yi, your xn term might become 0. Therefore, at most you can say that the degree of this entire polynomial is less than or equal to n. It cannot exceed, because each one is a polynomial of degree n. Thus, our first condition for interpolating polynomial is satisfied. Coming to the next condition, that is interpolating condition. Thanks to this property of the Lagrange polynomial, you can see that if you put x equal to xj, that is one of the node points, then what happens? You can see q of xj will be sigma I equal to 0 to n yi li of xj, right? So all terms for which I is not equal to j will vanish because of this condition, and one term surely will be there with I is equal to j, right? Because I is running from 0 to n and j is one of these integers, right? Therefore, I will surely be equal to j in one of the terms of this sum. In that term, you will have your L j of xj to be 1, and that will give you yj, because at that place yi will be yj, because I equal to j. So this becomes 1 and this becomes yj, and that will comfortably satisfy the interpolation condition. From here, you can see that q of x defined by this is an interpolating polynomial. Now, why should this interpolating polynomial be equal to Pn of x, which you took as an interpolating polynomial? Well, that is because of the uniqueness of interpolating polynomial. Lagrange constructed the polynomial q of x. You have a polynomial Pn of x. You know that your Pn of x is a interpolating polynomial. Now the question is whether Lagrange constructed polynomial is exactly your interpolating polynomial. The answer is yes. So they both are equal. How we proved? We first proved that the polynomial constructed in the Lagrange form is also an interpolating polynomial, and then we use the uniqueness property of interpolating polynomial for a given data set, and concluded that the interpolating polynomial that we have is precisely equal to q of x, which is what the Lagrange has proposed as an interpolating polynomial. So that proves the theorem. Let us just construct the Lagrange polynomial in the particular case when n is equal to 1. And in fact, we will also simplify the Lagrange form of interpolating polynomial to a form which later we will introduce as the Newton's form of interpolation. Let us take x0 and x1. That is, we have only two distinct node points. Once you give node points, irrespective to whatever may be the values that you are going to propose in your data set, you can immediately construct the Lagrange polynomials, because Lagrange polynomials doesn't depend on what value you give in your data set. It only depends on the nodes, right? So therefore, once you give your nodes, you can go ahead and construct the Lagrange polynomials. Here you are giving 2 points as nodes. Therefore, your Lagrange polynomial will be of degree 1. The first Lagrange polynomial, which is L0, will exclude x0 in the numerator and take other terms, and your denominator constant is also like this. And similarly, L1 will exclude x1 term in the numerator, and in the denominator you have the same thing but substituting x by x1, right? So that is how you construct. This is just a straightforward implementation of the general form of Lagrange polynomial. Once you have this, your Lagrange interpolating polynomial says that you can write your interpolating polynomial as y0 L0 of x plus y1 L1 of x, right? Here I am generating these values y from a function f. That is why I have just put f of x0 and f of x1 instead of y0 and y1 here, and simply substituting this value here and similarly this here and getting this, and just rewriting that term and bringing it to a form which later you will see that this is nothing but Newton's form of interpolating polynomial with n equal to 1. So here itself I am telling you that Lagrange form of interpolation and Newton's form of interpolation, well, they are not different, they are same. Even theoretically we have uniqueness which should justify that, and constructively also you can see that they both are happening to be finally the same polynomial. Let us take an example. If you recall, in the last class, we intentionally gave a bad example where the idea of interpolating polynomial doesn't work well. But now we will take an example where it works well. Let us take the function f of x equal to e power x and take 2 points in our data set, x0, x1, and thereby we will get the polynomial of degree 1. Let us use the Lagrange form to construct this polynomial. Our aim finally is to find the value of e to the power of 0.826, which is lying in between these 2 points, using the interpolating polynomial of degree 1. In the last slide, we have constructed this polynomial more precisely and put it in this form. Now let us substitute x0 is equal to 0.82, x1 equal to 0.83, and similarly f of x0 as 2.27 and so on, and f of x1 as 2.29 and so on into this expression, and we can write it in this form, and that's a polynomial of degree 1, which is given by this. Let us try to plug in x equal to 0.826 and see what is happening. Well, with the help of a calculator, you can also see the value of the exponential function at the point 0.826 is given by this. And now we will plug in x equal to 0.826 into this polynomial, and that gives us this value. You can see that this is pretty close to what is exactly the value of the exponential function. So thereby, this is a story where your interpolating polynomial works well even with degree 1. You can see that the relative error is very, very small in this case. And in fact, we will go to introduce one more point into our data set. So now we have x0, x1, and x2, and thereby we will get a quadratic polynomial as the interpolating polynomial for this data set, right? Now I'll leave it to you to construct the Lagrange polynomials L0, L1, L2, and then write P2 of x is equal to y0, which is this one, or f of x0, you can say, L0 of x plus y1 or f of x1, that is this, into L1 of x plus y2, which is f of x2 into L2 of x, right? So you just substitute these values into this Lagrange form of interpolating polynomial. First construct the Lagrange polynomials and then put them here and get the Lagrange form of interpolating polynomial, which will land up to be a quadratic polynomial. Then use x equal to 0.826. You can see that P2's value will be given by this. With that, you have much better relative error than what you got with the linear polynomial interpolation, where your relative error is given like this. So that gives us a feeling that you keep on increasing the number of node points. Say, for instance, you put one more point here, x3, similarly f of x3 here. So you may get a better approximation than P2 and so on. Mathematically, this is true. But when you go to compute these polynomials and their values on a computer, because of the arithmetic error, it is not always true that you keep on increasing the number of points in your data set, equivalently increasing the degree of the interpolating polynomial. It is not true that your accuracy in the approximation will keep on increasing. Again, I'll tell you, mathematically, well, it is true that if you keep on increasing the degree of the polynomial, the approximation quality or the accuracy will increase. But due to the presence of arithmetic error, as you go on increasing at one stage, your approximation will start going very bad. I'll give you example later, but for time being, we will go on with another form of interpolating polynomial, that is Newton's form of interpolating polynomial. Well, next let us see another form of the interpolating polynomial called Newton's form of interpolating polynomial. Again, I emphasize that the way we construct the polynomial is only different, but the final output is going to be the same. That is, the polynomial that we obtain finally will be the same as what we obtained from the Lagrange's form also. If that is so, the immediate question is, why are we thinking of constructing the interpolating polynomial in a different way? Why can't we just stick with the Lagrange form itself? Often what happens is you are given a data set with n plus 1 entries and you constructed the interpolating polynomial Pn of x. Later you found that it is not approximating your function as accurate as you want, And so you want to add one more node point into your data set, and thereby you want to go for the interpolating polynomial which is 1 degree higher in order to see if that meets your accuracy. Then if you go with the Lagrange form, the moment you put one more point into your data set, the entire Lagrange polynomials L0, L1 up to Ln plus 1, they all have to be reconstructed because they will be entirely different from L0, L1 up to Ln that were constructed using the first n plus 1 points. Okay, you can go back and see the formula and try to understand that if you include one point into your data set, the entire set of Lagrange polynomials will be different. And therefore, this polynomial, that is the polynomial of degree n plus 1 coming from n plus 2 number of points, has to be constructed right from the beginning. You cannot make use of the effort that you have put in constructing Pn of x, right? So that's the main drawback of Lagrange polynomial. However, Lagrange polynomial is very comfortable to be used theoretically. We ourselves will see in error analysis, we mainly use Lagrange form of interpolating polynomial. This is because in the Lagrange form of interpolation, we see that it is written as the linear combination of the Lagrange polynomials. So in a sense, you are taking the Lagrange polynomials as the basis and constructing the interpolating polynomial as the linear combination of these elements, right? So theoretically, it's very nice to be used, but computationally, it has such drawbacks. So what we want is, suppose you include one more point with the intention of increasing your accuracy, then it is desirable to somehow construct your higher degree polynomial with the help of the effort that you have already put in constructing the lower degree polynomial. Say for instance, Pn plus 1 of x, if you can write it as Pn of x plus something, then what happens is you can make use of the effort that you have already put, and you only have to put new effort in computing that extra term, right? So if you can write your polynomial in this form, that sounds more convincing computationally. And if you recall, this is not something new to us, because when we were proving existence and uniqueness, in fact, we followed this idea only. Let us go back and recall that you are given a data set consisting of n plus 1 points. How you prove the existence? Well, you want to obtain Pn of x. You assume that you already have Pn minus 1 of x, which is constructed using the first n points in the data set, and then you added a new term like this with a degree of freedom, and later you chose that degree of freedom by imposing that Pn of xn, that new point that you added into your data set, is equal to yn, right? Because this should also be a part of your interpolating condition, and the first n conditions are already guaranteed by your polynomial Pn minus 1 of x, right? So when you impose this condition, you can see that the constant c that you have introduced in this form will be given by this expression, right? This is already known to us. And this is, in a sense, is the basic idea behind constructing the Newton's form of interpolating polynomial. Let us put this form of interpolating polynomial in this theorem. Given the data set consisting of n plus 1 points, the interpolating polynomial Pn of x can also be written in this form, where a0, a1 up to an are constants. Now you can see that the polynomial with 1 degree less, that is Pn minus 1 of x, is written like this. Given that you have already constructed Pn minus 1 of x, to construct Pn, you just need to put this extra term. If you recall, this is what we have denoted by C in the previous slide, and you know how to calculate this C, and therefore you just have to put effort in just finding this one extra term, and this form of the interpolating polynomial is called the Newton's form of interpolating polynomial. Well, I will not go to prove it once again, because while proving the existence, we precisely proved that this is a interpolating polynomial, right? So therefore you don't need to repeat that proof here, but rather we will see how these constants are given. You can see that a naught is simply f of x naught. A1 is given by f of x1 minus p naught of x1, that is nothing but now f of x naught, right, divided by x1 minus x naught. If you recall, if you take up to here, that is nothing but therefore f of x naught plus f of x1 minus f of x naught divided by x1 minus x naught into x minus x naught. This is precisely what we have derived in one of the examples after introducing the Lagrange form of interpolation. If you recall, we started with the Lagrange form and simplified it to this form. And I have also remarked that this is nothing but the Newton's form, right? So up to here, you can see very easily that Lagrange is in fact same as Newton in the final form. In fact, this can be shown for all n. Like that, you can keep on going. You can find what is A2, A3, and so on. Note that A depends on the value of f at x naught. A1 similarly depends on the value of f at x naught as well as x1, because it depends on f of x1 through p naught, right? And if you go on like that, you can also see that A2 is given like this. And from there, we can write the general form of an, and an is given by f of xn minus pn minus 1 of xn divided by xn minus x naught, xn minus x1, and so on up to xn minus 1. And as you can see, a2 depends on f at the points x naught, x1, and x2, and so on. And in general, an depends on the value of f at the node points x0, x1 up to xn. That's very clear. Once you see these forms, well, you can observe that there is nothing really we are achieving through the Newton's form from the computational point of view. Why? Because if you see in the Newton's form, finally what we have to compute, we have to compute all these constants, AKs, right? And how AKs are given? AKs are given by this formula. And when you are computing Pn plus 1 of x, you can see that you have to compute all the constants A0, A1, and so on. And they all depend on the interpolating polynomials of lower degree, right? So that is where you really don't achieve much from the computational point of view, even from the Newton's form of interpolating polynomial. As I told, we need to know all the previous interpolating polynomials. Okay, when you are computing Pn, you need to know Pn minus 1, n minus 2, and so on up to P naught. Okay, everything should be known. Therefore, you need to anyway evaluate everybody and store them in the memory. So in that way, one can see, although I will not give any emphasis on operation counting here, but one can see that the total computational cost is in that sense equivalent to Lagrange form. So there's nothing great that we are achieving by putting the Lagrange form in this special form and call it as Newton's form. Now the question is it possible to compute these constants AK without storing all the polynomials of the lower degree? Because that is where precisely you are losing the computational efficiency. The answer is yes, you can do that. That is why Newton's form is more popular computationally. If it is just like what I have introduced as a Newton form, then people would not have even cared for going to Newton's form. But there is a way to again rewrite this form of interpolating polynomial that is computationally more efficient. For that, we need a concept called divided differences. Newton's divided differences, which we will introduce now.